All right, I'm recording now. Perfect. So yeah, okay. So let's start with the review. Okay, so David, you said problem number 11. All right. Okay. So this is problem 11 in the review sheet. All right, guys. Sorry, problem 11. So we have this S, which is a surface, and there are two integrals to evaluate. So the first integral. So first thing, guys. First, you need to know. You have to determine whether you have a line integral or you have a surface integral, right? So like in this problem 11, we have this surface S, and so we're gonna integrate over S, right? So here we are talking about surface integrals, right? So S, it's a surface, okay? So it's the surface, it's the closed cylinder with the bottom given by z equals to 1, the top given by z equals to 3, and lateral surface given by the equation x squared plus y squared equals to 4. All right, let me just graph quickly this S. You don't have to graph, of course, S, just to give you an idea about the graph of S here. So this is, let's say, x, y, and z. All right, so first thing, guys, here, this surface S, it's in the space, right? Because we have three coordinates here. We have x, y, and z. So this is a surface in the space, in R3. Okay, this is really important in R3. Anyway, so it's a cylinder, x squared plus y squared equals to 4, between z equals to 1 and z equals to 3. So like this is 1 here, and like let's say this is a 3 here. All right, and then you have your cylinder. So it's like, you have like a bunch of circles. All right, and so this would be your surface S. Okay. Anyway, so the first we have a scalar surface integral. So scalar surface integral, because inside the integral, so first you have to evaluate the integral over S of y dA. Okay, so here you can see inside the integral, it's a function. It's not a vector field, right? This is a function. So we have this function f of x, y, z equals to y, okay? So if you see inside the integral of function, then that will be, so then this is a scalar surface integral. Right? It's over surface S, so it's a surface integral. And inside the integral, we have a function, so it's a scalar surface integral. All right? Now, how do we compute or how do we evaluate such an integral? So there are, I would say, there are. So let me just remind you of the formula here. So the formula says the following. So this would be the formula. So by definition, this is equal to, if you have some function f, over integral of function f over surface S. So this should be equal to f along the surface S. So you need to parameterize your surface S. Okay. And then here times, it's a function, times the norm of TU cross TV. Okay, DU dV. Okay, so this dot here, this is a product between two functions, because you see, guys, I mean, f is a function, obviously, and this is the norm of this cross product. So a norm, this norm is going to be a function. So this is here, this is a product of two functions. Anyway, so the first step I would say is to parameterize. You see here, I'm using this phi of uv. This is the parameterization of S. So first step, step one. So what you need to do, step one, is to parameterize S. Okay. And when you parameterize S, so you need to be careful here. You need to be careful with the orientation. Careful with the orientation, because the orientation here is it's in the problem it's given. So we have to orient S with outward normals, right? Outward. So they are going out of the surface. So in this case, that would be these normals here. Okay. Okay. Okay, because again, the problem, it says orient S with outward normals, right? So my normals. So what we mean by normal? The normal is given by this TU cross TV. Okay, so the normal, when I say normal here, normal vector, it's the vector given by this TU cross TV. So this TU cross TV, it must be outward pointing normal. Okay. Anyway, so let's first parameterize S and then check the orientation. So I guess I won't do all the computations here. I mean, I won't compute the whole integral, but I'm gonna give you like everything you need to compute your integral. Okay. So first parameterize S. So S. Let me see here. Okay. So S is, it's basic. So it's this cylinder, right? X squared plus y squared equals to 4. Right, so it's x squared plus y squared equals to 4, and the z is between 1 and 3, right? So 1 and 3. All right. So to parameterize your cylinder, so we can use, so we need two parameters, right? So first, your x squared plus y squared equals to 4, because so we have circles, right? So circle of radius 2, so that would be x would be 2 cosine, let's say, of u. Y, it's 2 sine of u. Okay. So then, because when you do, if you do, so this is supposed to be my x, right? And this is supposed to be my y. So when you do x squared plus y squared, you get 4, right? That's exactly the lateral surface, right? That's my cylinder, right? That's why my x is 2 cosine of u and y is 2 sine of u. Now, there is another parameter. I mean, there is another variable, which is a variable z, right? So what would be the value of z? Well, there's no equation on z, right? So there's no restriction on z. The only restriction on z is that z is between 1 and 3, right? So this is sort of saying that's the domain of z. So my z is just some independent variable. So that will be my second variable or second parameter, v. Okay, but then so z must be between 1 and 3. So in other words, v must be between 1 and 3. Okay, so we have this. So this is my parameterization, right? And the domain, of course. So what will be the domain for for u? U is it's my angle. So it's because we have the whole circle. So u is going to be between 0 and 2 pi. So u is between 0 and 2 pi. And v, as I said, it's between 1 and 3. So that's my domain. Does this make sense to you guys? Do you see why this would be the parameterization of my cylinder? I mean, you take the equations and, you have x squared plus y squared equals to 4. Well, that's like just the equation of a circle, right? You only need one parameter, u, right? And then, of course, because we are in the space, right? This s, that's really important. So s is in r feet in the space. So we have the third, you have this third coordinate, which is z. And there's no equation. I mean, there's no restriction on z. The only restriction is that z is between 1 and 3. But that's like the domain. It's not like an equation satisfied by z. All right, so then z is like just a independent variable, and it's between 1 and 3. So again, guys, if you have questions, let me know. Okay, please stop me. I mean, if you don't feel shy, if you have questions, I mean, I'm here to answer your questions. All right. Anyway, so yeah. So this is parameterization. Now I need to. Second step, I would say, is to compute this TU cross TV and make sure that I have the right orientation. So compute TU cross TV, all right? And so make sure of the orientation. Okay. Anyway, so what's TU? TU is just derivative of phi, with respect to u. So this would be like this is supposed to be a vector. So it's like -2. No, sorry, the derivative of cosine. Yeah, sorry, cosine. Yes, -2 sine of u. 2 cosine of u. Wait, yeah. And then derivative of v is just 0. Now you need TV, which is derivative of phi with respect to v. So that'll be 0, 0, 1. You do TU cross TV. So cross product. So guys, I guess you know how to do the cross product. So that will be actually 2 cosine of u, and then 2 sine of u, and then it's going to be 0. All right. Okay, guys. Now make sure that you have the correct orientation, the orientation required by the problem, right? So again, the orientation here is supposed to be where is it? Outward pointing, right? So what you can do is you can take a random point on the cylinder and check if your normal is outward or inward, right? So let's say, for example, you're gonna take. So here's my cylinder, right? So let's say you're gonna take the point. I don't know. Let's say u. So here's my domain, right? U is between 0 and 2 pi, and v between 0 and v between 1 and 3, right? So for example, if you take u equal to, let's say, 0, okay. So let's say u is 0 and v is between 1 and 3. So let's say it's v is 1, okay? So what's phi of 0, 1? So that would be phi of 0, 1 would be a point on the cylinder, right? So phi of 0, 1. So here's my phi. So u here is 0, and v, we said it's 1, right? So that would be 2, 0, 1. So it's going to be the point 2, 0, 1. So this is the point, 2, 0, 1. Where's the point 2, 0, 1? I mean, if you want to plot the point 2, 0, 1, then it would be, so 2 in the direction of x, 0 in the direction of y, and 1 in the direction of z. So that would be this point here. Oops. So that would be, let's say, this point here. This is the point 2, 0, 1. Okay. And at the point 2, 0, 1, so the normal must be outward. So like in this direction here. Okay. So what's the normal at the point 2, 0, 1? Let's see. The TU cross TV is this That's my normal. This is my normal vector, right? This is my normal. Now, what's the normal vector at the point 201? So TU cross TV at the point 201. So at the point 201, you know, U is 0. This is U. U is 0 and V is 1. U is 0 and V is 1. So here it's U is 0. There's no V in TU cross TV. That's good. So that's 2 sine of 0, 0. So that will be the vector 2, 0, 0, right? So if you draw the vector 2, 0, 0 at the point 2, 0, 1, well, then that will be this vector. You know, that will be this vector here. If you start from the point 2, 0, 1 and you draw the vector 2, 0, 0, so that this one here, that will be my 2, 0, 0, and that will be my normal vector at the point 2, 0, 1. So it's outward. Okay, does this make sense to you guys? Really, I mean, please let me know if you have trouble, you don't see what I'm talking about, just let me know. I mean, I can. All right.
Professor, how did you get
yes. What?
200?
200. You see that here's my normal vector, right? TU cross TV. Right, that's my normal vector, and I picked the point. So I pick, like I said, well, let's take for example the point where U is 0 and V is 1. So U is 0 and V is 1. It gives you the point 201. That's my point. Now, if here in this normal vector you replace U by 0, you see here U is 0. So that will be 2, 0, 0, right? If you replace U by 0 in this normal vector, this is my normal vector here. You replace U by 0, you get 2, 0, 0, right? And so that's my normal vector at the point 201. It's the vector 2, 0, 0.
So why would we replace U by 0?
Yes, because I picked the point. You see, I picked the point. You can pick U. I mean, U is.
And I understand the how you got 201. It's about 200.
The 200. Well, yeah. I replaced U and U by 0 and V by 1 in the normal vector.
Okay.
Because
okay.
I mean,
it's because I saw you have under the normal vector you had size 0 and is equal to 201. So I was confused.
Yeah, no, because to get my point, to get this point P, which is 201, I had to replace U by 0 and V by 1, right? In the phi.
Okay.
Right here in the phi, to get the point 201, I had to replace U by 0 and V by 1. So, so what I'm saying is that at the point P, 201, the U must be equal to 0 and the V must be equal to 1. Okay. And of course, you can pick a different point. You can say, well, I can pick a point, I don't know. So U is between 0 and 2 pi, right? You can pick U pi over 2, for example. V is between 1 and 3, right? You can say, well, V is 3. Okay, so when you pick pi over 2 and 3, you're going to get a different point on the cylinder. Okay, you're going to get, I don't know, some another point. Let's say somewhere else. Here, for example, let's, for example, I don't know, let's say this point here. You get this point here, right? For U equals to, I don't know, pi and V is 2, you're going to get this point here, for example, different point, right? So each point on the cylinder, it corresponds to some value of U and the value of V, right? Whenever you replace U and V by some values, you get a different point on the cylinder. Okay, and then to find the corresponding normal at that point, you have to replace U and V by the same values. Okay. All right. So this is my so the rotation here is the right one. So the rotation is here is okay. Okay, so we don't have to reverse the rotation here. Again, guys, actually for the scalar surface integral, the orientation really doesn't matter, right? Because remember, guys, we said that for the scalar surface integral, the integral itself is independent of the orientation. Okay, it doesn't matter which orientation you're gonna take, you're gonna get the same answer. But the orientation matters for the vector surface integral, not for the scalar. So here in this case, actually, the orientation doesn't matter. But for the second part of the question, yes, the orientation matters. Anyway, so I compute TU cross TV, but you know, guys, for this scalar surface integral, we need the norm of TU cross TV, right? So we need the norm of this vector. So step, let's say this is step 3, for example. Now we have to find, let's say, the norm of this TU cross TV. So what's the norm of TU cross TV? I mean, TU cross TV, we said it's, where is it? TU cross TV, it's 2 cosine of u, 2 sine of u, 0. 2 cosine of u, 2 sine of u, and 0. So the norm, you have to take the square root, the sum of the squares. So like this is square root, like 2 cosine of u square plus 2 sine of u, sine of u, sine of u square plus 0 square, right? And then you trig identity to say that this is actually equal to 2, all right? That's the norm of my normal vector. Okay, so I got the norm. So now I can, in the last step, I can evaluate my scalar surface integral. Okay, so my scalar, so it's y dA, right, over s. So remember, phi of uv was 2 cosine of u, 2 sine of u, and v, right? So this y would be, so this is my x, supposed to be my x, this is supposed to be my y, this is supposed to be my z along along s, right? Along s, that's the values of x, y, z. So this y is going to be 2 sine of u, right? It's this value here. So that's my 2 sine of u. Okay, and now times, and now here is supposed to have the norm of TU cross TV, right? And then DU dV. Well, what's the norm of TU cross TV? We just said it's 2, right? So this is equal to 2 here. Now u is between, remember the domain, u is between 0 to pi, and v is between 1 and 3. And then you are good to go, right? This is easy to integrate. This is 4 sine of u, du dv, u between 0 and 2 pi, and v is between 0, 1, and 3, okay? And then, yeah, you have to finish the integral here, of course, but I won't do it because you know how to do this. All right. So this is the first part of the question, right? Is there any question, any other question about this first part, about this scalar surface integral? So as I said here, in the scalar surface integral, the orientation doesn't matter. Okay, so here it doesn't matter if you have the orientation required by the problem. Okay, so just remark here, just to say that the scalar surface integral is independent. Integral is independent of the orientation. Okay. Now, the second part of the question. So this is part 1. The part 2. So this is part 2. So in the part 2, you have to evaluate. You know, where is it? The flux, right? The flux of this vector field F, which is minus y, x, and 0 across S. Okay, so just to remind you, what's the flux? So the flux of F plus S. So this is supposed to be a double integral of the vector field F along S. Okay, now what's the formula for this? So this is defined as the double integral of f cross product with sorry, not cross product, but scalar product. Sorry, so scalar product with tu cross TV du. Okay, so this is a scalar. So over S, of course. So this is a scalar. This is a scalar product. So we have two vectors. So this, the dot here means the scalar product of two vectors. That's different from the when you have a scalar surface integral. Scalar surface integral, you have a product of two functions. The dot there means the product of two functions, but here the dot, it's the scalar product of two vectors. All right. So how to do this? Well, we got the TU cross TV. We know what's TU cross. We just computed TU cross TV in the first part of the problem. Now F along the surface S. So remind you again, phi of UV, the parameterization of S, right? We said it's 2 cosine of U, 2 sine of U, and then V, right? So again, this is supposed to be my X, this is Y, and here's my Z. All right, so let's do this. So we have, this is double integral. So my vector field F. So what's my vector field F? So it's minus Y X 0, scalar product with TU cross TV, TU cross TV, where is it? TU cross TV, 2 cosine of U, 2 sine of U 0. So 2 cosine of U, 2 cosine of U, 2 sine of U, and 0. All right, du, dv, u again between 0 and 2 pi, v between 1 and 3. Now you have to replace this y here. Y is equal to 2 sine of u. This x here is equal to this 2 cosine of u, right? So it's actually this double integral from 1 to 3, 0 to pi. So this is minus 2 sine of u. X is 2 cosine of u. 0. It's a scalar product with 2 cosine of u, 2 sine of u, and then 0, du dv. All right, so let's see. Well, actually, the answer here is very easy. It's going to be just 0, right? So this is, come on. So this is 1, 3, from 0 to pi. And then we have scalar product. You know, guys, how to do the scalar product. So this is minus 4 sine of u, cosine of u, plus 4 cosine of u, sine of u, plus 0, du dv. And of course, this thing here that cancel out. So this is just equal to 0. And that's the answer. All right. And here, well, here's 0. Well, in this case, actually, the orientation doesn't matter because the opposite of 0 would be just 0. But as I said, for the flux of F, the orientation is important. So you have to make sure that you have the correct orientation and used by your parameterization. Any question, guys? I don't see. I think in the chat there's something. Oh no, that's good.
Number 4.
Number four. Don't forget, guys, there's also Stokes theorem, right? In the test, right? There's a page 3 with the 12, problem 12 and 13. But yeah, let's move to the number 4. 4, yeah, Green's theorem. I mean, I know it's a lot of things, guys, but it's I mean, that's what it is. Okay, so problem number 4. So this is Green's theorem. Okay, so Green's theorem, just to remind you quickly, Green's theorem. So in Green's theorem, we are in the plane. We are not in the space. Okay, so we are in the plane. So
Yeah,
in the
so
plane.
what confused me about number 4 is that I was wondering, like, how would we parameterize the annulus because it's the
Uh, you mean the double
region
integral, right?
between the two. Yeah, it's the region
The double, like,
circles.
okay, yeah.
I was
So
wondering. So that's what confused me for number 4.
okay. Uh, so you just let me just write down here dx dy. So your question is about how to find the domain for this double integral, right? So let me just write down here Green's theorem. So this is so Green's theorem. So you have this double integral, which is equal to the line integral along the boundary of this, right? So your question is about how to parameterize the domain for the double integral, right? So for this dx dy. Well, it's the annulus. So it's so x squared. So let me just graph the annulus here. So we have these two circles. So this is my region D, right? And you have x squared plus y squared equals to 9. And this is x squared. So it's inside the circle x squared plus y squared equals to 9, and the other one is equals to 4. All right. So then R. So use polar coordinates, obviously, because we have circles. You will say, well, if you use polar coordinates, of course, x would be r cosine of t. Cosine of theta. Y is r cosine. R sine of theta. The angle theta is because it's just the whole annulus. So theta here obviously is between 0 and 2 pi. But the r, x squared plus y squared equals to r squared. So r is between. So the radius here obviously it's between. Here this is 2, right? Sorry, let's say the other. Well, the radius r here, and this one here, of course, the radius is r here is 3, right? So then the radius r, so r must be between 2 and 3 in this case. All right. You see how I parameterize this? How I found the domain. So here you don't have to parameterize. Here we don't parameterize the surface. It's not the surface in the space. Here it's a region in the plane. So all you have to do is to find the domain. And what I'm saying is that so when you use the polar coordinates, the theta is between 0 and 2 pi, and r is between 2 and 3. So that's how we parameterize this annulus. Between the circles, the two circles. Does this answer your question?
And then we just find
yeah. So then
yes.
Okay. So like here, I don't know. So let's see. So m. Sorry. Here it's the other way. Sorry, I wrote n here. So it should be n here. Sorry. And here m, of course. So n and m, that's like my vector field f. Supposed to first function, that's my m. The second function is supposed to be my n. So like here, let's see. So partial n, partial x. Let's see, partial n, partial x. So that will be minus y squared, right? Minus partial m, partial y. So that will be an x squared, right? Dx dy, right? Over d. So this would be. So what I'm computing, guys, here, this is the the partial n x minus partial n partial y and dx dy. Okay, this is the let's say the first side of Green's theorem. Anyway, so use polar coordinates. Of course, here use polar coordinates. Don't forget the polar coordinates. Don't forget the Jacobian, guys. Okay, so here that would be minus r squared sine squared of theta minus r squared cosine squared of theta. So then this dx dy is going to be now r dr d theta, right? Because of the Jacobian. Don't forget the Jacobian when you change the coordinates. So this is my Jacobian. And of course, I mean, R, as I said, R is between, 2 and 3, theta between 0 and 2 pi. So this is just a, I mean, sine squared, goes, of course, is 1. So this is just a minus R cubed, dr d theta. Right. Does this answer your question, Anicia?
So we don't need like
The other side?
Yeah, we don't need like C1 plus C2. Do we need
Oh,
that?
yeah. Oh, yeah. So this is for the,
that was what I was confused about. The other
Oh, okay, yeah, okay. So yeah, I see. You mean that now? So the other, so this is the first part of the theorem. Now the second part, the part 2, that's the, so the integral along the boundary, right? So this one here, ds. So this is the C. This is the boundary. All right. So the boundary. Well, it's just no. So the boundary of the annulus is going to be the union of 2 circles. Let me just draw again here. And you have to make sure that we have the correct orientation here. So the boundary. So let's call this first circle here C1 and this inside circle C2. Okay, so this is, so my integral, my vector line integral along the boundary is equal to, along the C1 plus, I don't have, okay, let me move to the other, so C2, I mean the vector line integral along C2. Okay, guys, in the Green's theorem, all right, you have to remember there's a orientation required by the Green's theorem. So the thing is the D, your region D, right? This is my D here. D must be on the left as one traverse the curve or the boundary. So like for C1, the orientation for C1 would be this one here, right? Because so it's counterclockwise, because in that case the D, you see the D would be D on the left. It's on the left of the orientation, right? D is on the left. Now the orientation for the circle inside the C2 is going to be actually clockwise. So for the other circle, this one here, the orientation is going to be clockwise, because so in that case D would be on the left, right? So D here, it's on the left of my orientation. All right. Does the orientation make sense to you? Remember, in Green's theorem, you have to orient the boundary, so that the region D is on the left of your orientation. Okay. Now, how to parameterize? You have to parameterize the curves here. I mean, like for C1, C1, it's just let's say gamma of t. C1 is just a circle of radius 3, right? So it's just 3 cosine of t, 3 sine of t, right? T between 0 and 2 pi. Okay. And C2. Okay, yeah, here, guys, you can check that. You can check that this is the right parameterization, because it induces the required orientation, right? Because so here the orientation here is correct. Is correct because, so as you can see, for example, when time t is 0, gamma of 0, what's gamma of 0? Gamma of 0 is 3, 0, right? If you can take, for example, t pi over 2, what's gamma of pi over 2? Well, it's just 0, 3. etc., etc. So so what we are saying is like what we are moving from the phi 0 to 0 phi, etc., etc. So that's exactly the orientation required by the by Green's theorem, right? So this is your, this is your phi 0 and this is your 0 phi, and so we are moving from phi 0 to 0 phi to negative phi 0, etc., etc. So that's exactly the orientation you need, right? Now the inside circle, the x squared plus y squared equals to 4. Of course, you may say, well, I'm going to just say, well, bit of t, 2 sine of t, sorry, not 2 sine of t, but 2 cosine of t, and then 2 sine of t, right? And you say, well, t is between 0 and 2 pi. All right, just a circle of radius 2. But that's not, but the orientation actually induced by this parameterization is the opposite to the one required by Green's theorem, right? Because this one here, it would be a counterclockwise. Okay, you can check it's going to be counterclockwise or rotation. But the thing we need inside the circle inside, I mean the C2, the orientation there must be clockwise, right? This one here, you see this one here? This is a clockwise orientation. Okay. So that's this parameterization actually doesn't induce the required orientation. So we need to change this. And the way to change in this case of circles, the easiest way is to change the t. So let me just say this is not this one. This is not, doesn't induce the required orientation, okay, which is clockwise rotation. So it's counterclockwise, but we need a clockwise rotation, right? So the easiest way would say, well, C2. So if you do alpha of t, and then change just the t to 2 pi minus t. Okay, 2 sine 2 pi minus t. Again, t is between 0 and 2 pi. Then I claim that this would induce a clockwise orientation. Okay, so then if you use this, then you're going to go from, let's say, from 2 0, then to 0 negative 2. So you're going to go from. So we're going to go from, so this, you start with the 2 0, but then you're going to go to 0 negative 2, and then you're going to go to what's that, negative 2 0, and then you're going to go to 0 2, etc. So that will be a clockwise rotation if you use this, the 2 pi minus t here. Okay. And then you know how to do the vector line integral, right, Anicia? I guess that's what you are asking. All right. Okay. Cool.
Professor, why did we change
the 2 pi minus t?
No, why did we change the coordinates of t from 0 to 2 pi to 0 to pi? When you change it from 2 pi to 2 pi minus t, you change the t from 0 to, is that pi? 0 to pi?
No, it's 2 pi there. Sorry, this is 2 pi. It's still the same interval. Yes, it's 2 pi. Yes. But my point is, if you do, of course, alpha 0, that would be 2 0. Okay. But if you do alpha, for example, pi over 2, I claim that this would be 0 negative 2. And if you do alpha pi, for example, that would be negative 2 0. If you do alpha 3 pi over 2, that would be 0 2. Of course, alpha 2 pi would be the same as alpha 0, right? So you have your circle, and so you start at 2 0, but then you go to 0 negative 2, and then you go to negative 2 0, and then you go to 0 2. So it would be clockwise. You see what I'm saying? That's why I changed, but the interval is the same. T is between 0 and 2 pi.
Okay.
Mhm. Any other questions, guys?
Number 13 for me.
Yeah, probably the Gauss theorem. Sorry, not Gauss theorem. Stokes theorem, right? 12. Oh, okay. David, you asked for 12. Anissa, you asked for 13. You have like, okay.
Do 13 is fine.
13 is fine. I mean, both
Yeah.
are about that Stokes
Maybe
theorem.
next time, Professor, you can like give a solution sheet. Because
A solution sheet.
that's a lot more.
That would be too much work for me. Actually, I mean, these problems, they can take a lot of time actually to do. I mean, I just figured out that I mean, well, probably because I gave like a lot of details, but yeah, for sure, these problems, they can take a lot of time. I mean, just to do one problem, it could take like I don't know, like at least 25 minutes, a half hour. Yeah, I mean, anyway, so. But the solution sheet would be too much. I mean, a lot of work for me, I guess. Okay, so let's go with that 13. I think it's a nice problem. Problem 13. Again, it's in the review sheet. Well, so we start with so we have to evaluate this the curl of the vector field F over the surface S. So what's S? S is, let me just write down here for you guys. So S is this surface. So it's given by, so it's the graph. So Z equals to 4 minus 4x squared minus y squared. And you need Z to be positive or 0. So I mean, 4 minus x squared minus y squared, this is sort of a paraboloid, right? A paraboloid which opens down, right? So, I mean, if you want to graph this surface S, so the highest point in the surface S is when x and y both are 0. So x and y both are 0, then Z would be 4. So that would be actually the vertex of this paraboloid. And so we're going to have this. When Z is 0, of course, this is x, y, z here. When Z is 0, it's not exactly a circle. When Z is 0, you have an ellipse, right? 4x squared plus y squared equals to 4, right? So when Z, let me just write it down here for you. So when Z is 0, you have 4x squared plus y squared equals to 4. All right, so that's not exactly it's not a circle, it's an ellipse, right? So here in the bottom, oops, where's the red? Oops, come on. So here, right, and so you have this. So we have this sort of a paraboloid. Okay. All right, so that would be my surface S. And what's the boundary of S in this case? It's going to be this ellipse here when Z is 0. So the boundary is this one here. This is the boundary of S. Okay. So this is C, which is the boundary of S. Anyway, and of course here, because Z is positive, Z is, we are saying Z is positive, right? It means that because Z is the 4 minus 4x squared minus y squared, okay, so this must be positive. So in other words, 4x squared plus y squared is less than 4, less or equal to 4, right? And this is like this will be like the domain of your domain for your surface S. Anyway, so you want to evaluate this double the curl of F, this one here, ds over the surface S. So first, I guess first step would be to find compute the curl of F. So step 1, let's compute curl of F. So that will be equal to, where's f? Okay, well, I don't want to, okay, I don't have the answer for this, but, and I don't want to give you all the computations because that will be, it's going to take too much time otherwise. But let me just do it very quickly. So the curl of f, I guess you know how to do this. So x, here it's x cubed, here it's e y squared, and here it's z e to the xy. All right, so this would be equal to, so the curl, so derivative with respect to y minus derivative with respect to z. So derivative with respect to y is going to be x z e to the y. Now for j, it's going to be 0 minus y z e to the xy. And then for k, derivative with respect to x is 0 minus derivative with respect to y is 0. So this would be 0 here. All right. So I guess, guys, you know how to do this, right? This curl of f, this just cross product of the del operator with the vector field f. Okay, so okay, that's good. Now, next step I would say is to try to parameterize s. Okay, so step number 2. Right. So again, you want to evaluate this this integral, right? So you need to find curl of f. You need to parameterize s, and then you need to find, of course, here it should be, the formula that says this is actually you need the tu cross tv. You need the normal vector. Okay, so so in the step number 2. Step number 2. So we need to parameterize s. Parameterize s. So here s is it's very simple to parameterize because it's a graph of some function, right? I explained this many times. I mean, what's s? S is given by z equals to 4 minus 4x squared minus y squared, right? So here, this is a graph of a function of xy, right? So this is like saying z is my f of xy, and my f of xy would be this 4 minus 4x squared minus y squared. Okay. So if you can express z in terms of x and y, so then your surface is just the graph of some function f. Okay, like in this case. Anyway, so why this is very simple to parameterize, because then phi of uv. So here's suppose my x, y, and z. So I need to parameterize this in terms of u and v. So x. So the only relation I have is this one. All I'm saying is that my z must be equal to this. Okay, so this is sort of like just a condition on z. So there's no like there are no conditions on x and y. So x and y are like independent variables. Okay, so you can say, well, my x is some independent variable u, my y is also an independent variable v, but then z must satisfy this equation. So z is 4 minus 4x squared, but x is u, so that's 4u squared minus y squared, but y is v, so that's minus v squared. All right. Now, what will be the domain of this? The domain for u and v? Well, remember, guys, we said because z must be positive, or 0, so then 4x squared plus y squared is less than 4. Okay. So 4x squared. So for the domain, uh, 4x squared plus y squared is less than 4. So in other words, 4u squared plus v squared is less than 4. So this is my domain. Okay. It's not exactly, so the domain here is not exactly the inside of a circle. It's inside of the interior of the ellipse. Okay, it's not the interior of a circle. Anyway, so I got my parameterization. Now I need to compute my normal vector. So I need to compute t u. So that will be the vector derivative with respect to u. So 1, 0, minus 8u. Derivative with respect to v, 0, 1, minus 2v. Okay, now TU cross TV, TU cross TV. So it's gonna be 0 minus or plus ATU. What I'm saying. Yes, correct. Minus plus 2V and then 1. All right. Now, make sure that you have the orientation induced by the surface S is the correct one. So S here is your oriented. So in the problem, it says oriented by a normal with a non-negative K component. Okay, so in your normal vector, so here, this is my normal vector. This is my normal vector. So the K component must be non-negative. Well, it's equal to 1, so it's not negative, right? So normal vector. So this corresponds to the orientation required in the given by the problem, right? So the orientation here. So here, this is the K component. K component means K here, it means the vector 0, 0, 1, right? When you say K, the vector K, that's the vector 0, 0, 1, right? We have I, J, and K. So this is the K component. All right, so K component is negative, is non-negative, it's positive. So then the orientation is okay. So the orientation induced by this parameterization is the orientation required by the problem. All right, now you want to compute your curl of F. Okay, now last step, which is step what? Step 3. Okay, so now we have all the ingredients. We have everything we need to evaluate. So now I can evaluate my curl of F, ds here over S. So this is, curl of F, scalar product with TU cross TV, du dv. All right. What's the domain? Domain here, so 4u squared plus v squared must be less or equal to 4, right? That's the domain. Remember the domain here? We said 4u squared plus v squared less than 4. That's the domain. All right, so let's see. So curl of F. Curl of F, let me just write down here, curl of F. That was in the first step. Let's see, curl of F, where's the curl of F? Well, it's x, z, e to the y. X, z, e to the y. No, x, z to the, sorry, x, z, yeah. Is that true? Let me see here. Why do I have, I forgot the x, right? No, sorry. Wait. Did I do a mistake here? No, I forgot the x, sorry. Yeah, here I forgot the x, right? So derivative of, yeah, there's an x, but you keep the xy in the top. Okay, that's cool. Now why do, okay, and this is minus, okay, that's correct. Yes, okay, cool. Okay, that's correct. So I just forgot the x there, guys. So xz e to the xy, e to the x, sorry, e to the xy. The second component is minus yz e to the xy, minus yz e to the xy, and then 0. Okay, that's cool. At least this is 0. The parameterization phi of uv, we said it's just u, v, and then z is the z is would be 4 minus 4u squared minus v squared. So u and v, and then 4 minus 4u squared minus v squared. This is v, of course, and this is u. And what else? Yeah, tu cross tv is just right here. So, all right, so we have everything now. So this double integral over this 4u squared plus v squared is equal to 4. Now, what would be a curl of f along S? Okay, along S, x must be equal to u, y must be equal to v, and z is equal to this whole thing here. All right. So then my curl of f along S would be, so x times z. So x is like u, z is this whole thing here. E to the xy. So that's e to the uv. And then what else? Minus yz. So minus like v times this whole thing. E to the xy, so that's e to the uv 0, scalar product with tu cross tv, which is atu 2v1, and then du dv. Okay, so this is going to be very horrible actually, and very complicated. That's the point of this exercise. So this thing here is going to be very complicated to integrate. You have this thing here times the 8u, so it's like, it's like 8u squared 4 minus 4u squared minus v squared e to the uv, like minus 2v squared 4, like minus 4u squared minus v squared e to the uv, plus plus 1 times 0 is just 0, du dv. But the thing is, as I said, this is gonna be very hard to compute. Okay, I can just wish you good luck if you want to compute this. This is very hard to evaluate. Okay, why it's hard? Because you have this exponential uv, but then you have this u to the power 4. You have this u squared v squared. It's gonna be very, very complicated to integrate. Okay. So hard to evaluate. Now, if it's hard to evaluate, then we can try to use Stokes theorem, right? So by Stokes theorem, normally this would be equal to. So it's hard to evaluate. Okay, so let's find the smarter way, easier way to evaluate this integral, right? So let's try to use Stokes theorem. So what does it say, Stokes theorem? Well, Stokes theorem says that this is. So this curl of f along S would be just the vector line integral, the flux of f the vector line integral of f along the boundary of S. Okay, so let's try to compute this. Okay, let's try to evaluate. So this one is hard. So let's see. So let's evaluate this vector line integral here. Okay. All right. Well, so we have to parameterize. So I would say the first step is to parameterize the boundary. So parameterize, step 1. I have to parameterize the boundary. Okay, so what's the boundary? Well, we said, so here's our my surface S, and so the boundary, we said there's just this ellipse here. Okay, this is delta S. All right. Now, guys, because you're using Stokes theorem, so we have to make sure that your the orientation of the boundary is consistent with the orientation of the surface S. The surface S, we said it's oriented by this normal with non-negative k component, right? I mean, this is supposed to be non-negative k component, so the direction of z is positive, right? So so just make sure, you have to make sure at some point, because you're using Green's Stokes theorem, make sure that the orientation of is consistent with the orientation of S. Okay, so to make sure that this is consistent with the orientation of S, remember, guys, we need to use the right-hand rule. So your the fingers of your right hand, they must curl in the direction of the orientation. Okay, so your thumb, your thumb points along the orientation of the surface S. So that would be my the normal vector. Okay, this is my normal vector, right? And so I'm using my right hand, right? So my thumb points along the orientation of S, the normal vector, all right? And now my index finger points along the orientation of the boundary, okay? And the middle finger, points inside the boundary. So in that case, so the orientation of the boundary must be counterclockwise. Okay. Okay, because my thumb would be my normal vector, the red vector, and then my index finger would be the green vector, right? And then my my middle finger would point inside the it's inside the boundary, right? Okay, so we have to parameterize this. Well, it's an ellipse. So what's this ellipse? So the boundary here is this ellipse. So we have, so this is when z is 0, right? So z is 0, z is 0. So then, you have 4, where is it? 4x squared. Where is it? So you see here, guys, so the boundary, the z is 0, because the boundary lies on the xy plane. So so 4 is equal to 4x squared plus y squared. So z is 0. So 4x squared plus y squared is equal to 4, right? So if you divide by 4, that will be x squared plus y squared over 4 equals to 1. In other words, that would be x squared plus y over 2 squared equals to 1, right? So how do we parameterize this? Well, this is just, we can use the cosine and sine. So in that case, so x would be, cosine of theta or cosine of t. Y over 2 is sine of t. Okay, so because, guys, you see, when you do, if you do x squared plus this y over 2 squared, that will be equal to 1, right? Cosine squared plus sine squared would be 1. And that's exactly the equation of my ellipse, right? And then, of course, so in other words, x is cosine of t, y is actually 2 sine of t. And what will be z? Well, z is just 0 because we are on my ellipse lies on the xy plane, so z is 0. And t, of course, here between 0 and 2 pi. All right. And you can check this, actually, this parameterization and use a counterclockwise orientation. So the orientation needed, required by the orientation here. So this end uses a counterclockwise orientation or rotation. Okay, and that's exactly what we need, right? But that's exactly what's required by the Stokes theorem. Okay, so the orientation is okay here. So orientation is okay. All right, now so what's okay, yeah, so let's now come back to this integral. So the step, I don't know which step here is going to be. So step 1, so now step 2, I can evaluate my vector line integral. So step 2. But then the point of this exercise, guys, is that this integral 2 is going to be kind of hard to evaluate. So, sorry. So my f, my vector field f, it was, you know, it was x cubed, was e y squared, was z e to the xy, right? So I want to evaluate this vector line integral along the boundary of S, here ds. All right. Don't forget. So here, my parameterization here, I forgot to say. So gamma of t, of course, would be cosine of t, you know, 2 sine of t, and then 0, right? Now this integral, guys, so it's gonna be f of gamma of t, scalar product with gamma prime of t, dt, t from 0 and 2, from 0 to 2 pi. Right. So now, what's f of gamma of t is going to be very complicated, and that's the why we. So 0 2 pi f of gamma of t. So x along gamma, x is cosine and y is 2 sine. So that would be like x cubed. So that's like cosine cube of t, e to the y square. So it's like 4 sine square of t. And then z is 0, right? Z is 0 along the path gamma. So I have 0 here, which is perfect. So scalar product with the gamma prime. So derivative of cosine, it's minus sine. Derivative of sine is cosine, and then 0 dt. Again, this is gamma prime of t, guys, right? This is gamma prime. This is gamma prime, okay, gamma prime dt. And so, well, but this is going to be still very complicated to compute because you're going to have like minus sine of t, let's say cosine cube. This is not bad because derivative of cosine is sine. So you can use substitution here. So the integral of this would be like cosine to the power 4. But the problem, I would say, the problem is in the next part, which is plus 2 cosine of t e to the power 4 sine square of t dt. Okay, so what's the problem with this second part of this integral here? Well, I mean, this is sine squared. Derivative of sine square, it's not just cosine. Derivative of sine square, it's sine times cosine, right? So even if you use a substitution here, it won't work. You need more. I mean, you need more work to actually to evaluate this integral. So this is kind of this part here. This first part is okay, the sine times cosine cube, but this one here is kind of hard to compute, to integrate. I mean, it's gonna take at least 3-4 substitutions. So this one is kind of hard to integrate. Come on. All right, does this make sense to you guys? I mean, why this is hard to integrate? It's just because, again, it's a sine square here is a power of exponential. So as a derivative, you need sine times cosine, not just cosine, if you want to use substitution. So you need to do like more than one substitution for sure. So that's kind of hard to integrate. So the idea here, as it says in the hint, if it's hard to evaluate, argue that you can integrate over another surface. And that's what I tried to explain on Tuesday. So in this case, if both integrals are kind of hard to integrate, you can try to integrate over a different surface. So the idea now, all right, so let me graph again my surface S. Oops, this should be. As you can see, this problem is taking more than half an hour. Well, anyway, so then it means that the next time I'm going to do, I mean, after the test Thursday next week, we have to do the Gauss theorem before do the review of the final. But anyway, the final is just final test 1 plus test 2 plus Gauss theorem. So this surface S, all right, this is your surface S, where this is a boundary. is your boundary here. And here's my surface S. And this is. So this is my surface S, and the yellow curve, that's the C, that's the boundary of S. Okay, so what you can do, guys, I'm gonna change, I'm gonna consider another surface, which is the most obvious one here in this case would be actually to take the inside of the ellipse. The inside of the ellipse is a surface. I mean, the ellipse itself, it's a curve. It's one-dimensional space, right? A curve, ellipse or circle, it's just one-dimensional. But if you take the inside of the circle, or the inside of the, like inside of the circle would be a disk, right? Or inside of the ellipse. So the inside of the ellipse here, that would be a surface. That's a surface. It's not just like one-dimensional space now. It's a two-dimensional space. So the inside of this ellipse, it's a surface. And let's call the inside of this, the inside of this ellipse S prime. Okay. Now, why I'm doing this? Because, well, if you use the Stokes theorem, so the thing here, so the idea here is that the boundary of S is the same as, is equal to the boundary of S prime. Okay, so the boundary of both surfaces is this, the ellipse, right? This is equal to C, and this is my ellipse, right? This is the 4x squared plus y squared equal to 4. That's my ellipse, right? So you see the surface, the blue surface and the green surface, both they have the same boundary. So again, the green surface is the bottom of your, you know, of your paraboloid, of your green, of the green surface, the blue surface, right? So the green surface is just like the bottom of the blue surface. Okay, now, so why this is useful? Because, so what we are saying is that, so we use the Stokes theorem. So we had to evaluate this curl of F, right, along S. Okay, but as I said, this turns out to be hard to compute, and so we try to use the Stokes theorem. So here we are using Stokes along the boundary of S, which is this C, this ellipse. So this is ds, all right, but this curve C is also the boundary of this S prime. So I can also use here, so this would be also equal to, so by Stokes theorem, this is also equal to the double integral of the curl of F, but this time over S prime. Okay. So again, because this S prime, the boundary of S prime, if you use the Stokes theorem, boundary of S prime is also this this ellipse C. So S and S prime, they have the same boundary. You see the idea here, guys? I mean, I don't know if this is clear for you. All right, so why? Okay, so now we're gonna use this surface S prime to evaluate our initial integral, right? This is my initial integral, right? So we said this is hard to compute. I try to use the Stokes theorem, but this vector line integral is also hard. And now I'm going to use Stokes theorem to say, well, this boundary is also the boundary of a different surface. So I'm gonna try to evaluate this. Okay, let's see what's the value of this, and let's see if it's hard. Also, it's also hard to evaluate. Well, the thing is, it's going to be kind of easy to evaluate because of the following. So what's S prime? Well, S prime, as I said, it's this 4x squared plus y squared. So it's the interior of the ellipse. So it's less or equal to 4. Okay. So when you use less or equal, it means it's the interior of the ellipse. Okay. It's not equal, it's less or equal. So it's an interior of the ellipse, right? This is the interior of the ellipse. All right, or in other words, you know, because I'm going to use polar coordinates to parameterize S prime. So this is, as I said, less or equal to 1. Okay. So first step, I wanna evaluate this curl of f along S prime. So I want to evaluate curl of f along S prime. Okay. So first, step 1, I would say, is to parameterize the S prime. Step 1, parameterize S prime and make sure that you have a consistent orientation, of course. So this is step 1. So parameterize S prime. Okay. So I'm going to use polar coordinates. So phi r theta. You know, if you use polar coordinates, so it's like saying, you know, this is like x would be r cosine of theta, and y over 2 is r sine of theta. So in that way, if you do x squared plus this y over 2 squared, then that will be r squared cosine squared plus r squared sine squared. So then r squared would be less than 1, which means that r is less than 1. Okay, so so my x, it's r sine of theta. Y, well, here, so just be careful, it's y over 2, which is equal to r sine of theta. Okay, so then y is 2r sine of theta. 2r sine of theta. Okay. And what about z? Well, this is surface S prime. Well, it lies on the xy plane, right? It's just the interior of my ellipse, which lies on the xy plane. So the z is just 0. So the z is just 0. Now, if you do the, you know, the normal vector, so tr, you know, this is supposed to be minus r sine of theta. So derivative with respect to r, first parameter, derivative with respect, sorry, this is, I derive with respect to theta here. So this is cosine of theta, 2 sine of theta, and then 0. Now the second normal vector, sorry, the second tangent vector, derivative with respect to theta. So that's my r sine of theta, 2r cosine of theta, and then there's 0. Now, my normal vector is tr cross theta. So that will be equal to, so this is just 0. And then, let's see, it's also 0 here. And then 2r cosine square plus 2r sine square. So it's going to be 2r. Okay. Of course, here, guys, theta, the domain. So theta is between 0 and 2 pi, and r, because, you know, if you do here, r square cosine plus r square sine, sine square less than 1. So then r square is less than 1. So r between 0 and 1. Okay. Anyway, so this normal vector, also we have to make sure that we have the consistent orientation, guys. So remember here, my curve C, my S, the orientation of S, oriented by normal the non-negative K component, right? My S was, the orientation of my S was this one here. Oops, come on. You know, a non-negative K component. The orientation of the curve C was, we said it's counterclockwise. right? Now, what about the orientation of S prime? It must be consistent with the orientation of the, of the boundary C, right, which is counterclockwise. Well, the orientation of S prime also is going to be actually, with non-negative K component. So it must be in this direction here. Okay, that's the orientation of S prime. And this TU cross TV, as you can see, TU cross, sorry, not TU cross TV, but TR cross theta, it's 0, 0 to R, but R is positive. So this is, it has the non-negative K component. This is non-negative. And that's exactly the same orientation. The orientation needed, consistent with the orientation of the boundary, non-negative K component here. Because R is positive, radius is positive, of course. All right, I got my TR cross theta, so now I'm ready to evaluate my integral, right? So now step 2, I know the, step 2, again, guys, I need to evaluate this over S prime, the curl of F. So this is supposed to be, so curl of F, scalar product with this TR cross theta, right? dr d theta. Okay, R is between 0 and 1, theta is between 0 and 2 pi. All right. So what's the curl of F? Remind you, curl of F was, what was the curl of F? Let's come back. What is the curl of F? Curl of, and then this is F, it's not the curl of F. I need the curl of F. The curl of F was somewhere right here. All right, so it's xz e to the xy, xz e to the xy, xz e to the xy minus yz. So xz minus yz, xz minus yz. So the curl of F was xz e to the xy minus yz e to the xy, and then 0. Okay. Parameterization of, remember, x must be r cosine, y must be 2r sine of theta, and then we have 0. Okay. So let's see. So then my integral would be equal. So we have this is 0 to pi, this is 0, 1. So the curl of F along this S prime. So along S prime, it means that X is this, Y is the 2R sine, and Z is 0. So, well, the curl of F would be, so this is also 0. So, I mean, Z is 0, right? So the curl of F would be just 0. So this is actually equal just 0, 0, 0, right? Because again, Z is 0 on S prime, right? And cross scalar product with dr theta, which is this 0, 0 to R, dr d theta. But this is actually going to be just 0, because this is just the vector 0, right? So it's going to be just 0. So the answer here is 0. Okay. So what we are saying, guys, is that my initial integral, where is it? Make sure that my curl of, all right, so where's my curl of F? Just make sure that this is 0. Yes. Okay, yeah, so what we are saying, guys, is that, so the conclusion is, that my initial integral, which is the curl of F along S, okay, which turns out to be hard to evaluate, this is by Stokes theorem is equal to the by Stokes theorem is equal to this vector line integral. So the vector line integral, so the integral of f along the boundary of S, which is the C. And this integral is also, we saw that this integral is also hard to compute, hard to evaluate. This is hard to evaluate. This is also hard to evaluate. But then this C, this boundary C is also the boundary of another surface, which is our surface S prime. So this is also by Stokes theorem. By Stokes theorem. This is also the double integral over S prime, okay, of the curl of F, which turns out to be 0. Okay. And so that's the answer. So the answer is our initial integral is actually equal to 0. I guess you are kind of probably lost a little bit, guys, but it's not that bad. I mean, if you, again, if you try to follow all the steps I did, you see it's not that bad. It's long, but it's not, I don't think it's that bad. Is there any question, guys? You see how this, like in problem number 12, both sides of the Stokes theorem, they're gonna be easy to evaluate. So so if you do this side here, this integral here is gonna be easy to evaluate. The same for this one. So you can compare, you compare the two integrals. So then you can verify Stokes theorem, right? But like in this problem number 13, so what we are saying is that like both sides of the Stokes theorem are hard to evaluate, right? Using this surface S. But this is but then we can use the power of the Stokes theorem by using a different surface, which has the same boundary as the original surface, right? The boundary is, of course, is this ellipse here. And so now our new integral is it's straightforward. There's just 0 actually, you see?
Professor, so how many of these questions will we be getting on the test?
That's a good question. I don't know yet. That's and it seems like to me like 2 hours is not enough. I mean,
this took you
like one like this.
half an
I
hour.
started sorry.
I mean, this question took you half an hour, so you us.
Right, like I started like I was looking to my watch, to the clock, and it was like I think 10 to 11 or something. So it took me like 45 minutes actually. Wow. But because I'm giving all the details, I guess. But still, yeah, it's a lot. So I don't know yet. I'm gonna decide this weekend, I guess. I'm gonna try to see how much time is gonna take me to do the problems, and probably multiply that by 2 or something, but I would say at least you would have 5 problems. I mean, we'll see. I would say 5 problems because they are, yeah, the problems here are kind of long, which means that we don't have time to start Gauss theorem, and that's really bad. It's not bad. I mean, it's okay. I mean, the important thing, guys, is that you get the picture here. You understand what we are doing. So I guess then the plan would be like, so we're gonna have the test on Tuesday, and then on Thursday, we're gonna have a review for the final, but it's very short review because again, the final is supposed to be a combination of the first and second test. So there will be no new material, but except the Gauss theorem. So I need to do the Gauss theorem. So I would do it next Thursday, and it's gonna be in the final. So next Thursday, I will start with the Gauss theorem. I have to finish Gauss theorem, and then if we have time, left, then I'm gonna do like a sort of a very quick review for the final. Well, we still have like 12 minutes. I don't know if you have another questions, guys, about the review sheet. We still have time.
I think someone had number 12.
Oh, someone wrote some. Oh yeah, David. Yeah, I can do 12 too. It's just similar to this problem. It's just that the integrals, the first and the second integral, kind of easy to evaluate. Yeah, I can go over 12 very quickly, unless you guys have another request. Okay. Oh well, I can do then 12.
Yeah, 12 looks good. I'm checking the other
Okay.
one.
Okay. Perfect. Makes sense because I mean, this Stokes theorem, again, it's not easy theorem. And I mean, well, we did a couple of examples, but still, yeah. Okay, so verify Stokes theorem. Sorry, verify Stokes theorem for the surface S. So S is so first, always, I would say the first step is to parameterize your surface. Once you parameterize your surface, you can compute your normal vector. You compute the curl of f, and then I guess you're good to go. Okay, so S is supposed to be x squared plus y squared plus 5. Z equals to 1. Z is positive, so this is like this is the portion of the graph. So here, guys, you can see I can express Z in terms of X and Y. So then Z would be, I mean, 5Z would be, of course, 1 minus x squared minus y squared. So then Z would be 1 over 5, 1 minus x squared minus y squared, right? So in this case, I can express Z in terms of X and Y. So here I have a graph of some function f, right? So Z in this case is f of xy, which is 1/5 1 times 1 minus x squared minus y squared, right? And of course, we are saying Z is positive, so which means, so with Z, which is 1/5, it's 1 minus x squared minus y squared, this must be positive, right? So in other words, x squared plus y squared would be less or equal to 1. Okay, so this is like my domain. Anyway, of course, you can try to, I mean, if you want to graph this surface S, is just sort of, again, just sort of paraboloid. So the highest point here would be a paraboloid which opened down. It opens down, guys, because you see here it's minus x squared minus y squared. So you're subtracting positive numbers. So it must be it opens down, right? So it's something like this here. And the boundary would be this circle. So here's my surface S. So my surface S. Okay. The highest point would be when X and Y both are 0. That would be 1/5. So that would be the highest point, but it doesn't matter. Okay. But what's really important for you guys is to parameterize first this S and to parameterize later the boundary of S. Okay, so the boundary is just this circle when Z is 0. So when Z is 0, of course, you're gonna have the circle x squared plus y squared equals to 1, right? I mean, it's just if you use Z is 0 here, x squared plus y squared equals to 1. Okay, so that would be the boundary. It's just a circle for this one. All right, so let's first step 1 parameterize. Well, we can compute the curl of f first, but it's up to you. Let's parameterize first. Oh yeah, I forgot to say, so this S oriented by upward normal, right? So upward normal, so that would be this normal here. Okay, it's upward. All right, so let's parameterize. Parameterize S as usual. So this is the graph of a function. As I explained many times, X is U, Y is V, and then Z is given by my function F, which is 1/5 of 1 minus U squared minus V squared. right? Let's check now the orientation. TU, it's 1, 0, minus 2/5, right? TV, sorry, minus 2/5 U here. I forgot the U, sorry. V 0, 1 minus the same here, 2/5 V. All right, so if you do TU cross TV, that would be 2/5 U, 2/5 V, and then 1. Okay, so you see here upward normal. In some sense, it means that this K component is is non-negative, because in the Z direction it's positive 1, which means that we have to go up. So your vector is going to go be pointing like upward pointing, right? So, or you can take a point, for example, I don't know, let's say you can take a point. So the domain is, I forgot to say it. So the domain, we said the domain was the domain. Domain, we said it's x squared plus y squared less than 1. So that means u squared plus v squared is less than 1. So the domain is the domain here. I forgot the domain. So x squared plus y squared less than 1. So then u squared plus v squared less than 1. Less or equal to 1. Okay. So for example, you can take the point u equals to 1, v equals to 0. So then your normal is going to be upward pointing. Okay, so just to say this is the correct, so the orientation here is correct, is okay. So this vector here, this is non-negative K component, so it's upward pointing, normal. Okay, so the orientation is okay. All right, now I need in the second step to compute the curl. Step 2, curl of F. I don't have the answer, so I have to do it very quickly. Portion X, portion Y, portion Z. What's X, Y, Z? What's the vector field F? So it's XZ. YZ, and then x squared plus y squared. So the curl of F would be 2y minus y, that would be plus y. Now for J would be x minus 2x, that's nice, that's minus x, and hopefully the last component is 0. And yes, last component is 0, that's the perfect problem. So that's the curl of F. Okay, and so this is step 2, and then we are good. We are good to go, and we can compute our step 3. So we can evaluate the curl of F. So this is a curl of F. Scalar product with TU cross TV, DU, DV. As I said, u squared plus v squared domain, u squared plus v squared less or equal to 1. So so the curl of F is y minus x. So the parameterization, guys, remember phi of uv. So we said u, v, and then z is 1/5 1 minus u squared minus v squared, right? That's the parameterization. Now, so my curl of F along S, so this y must be equal to v, x must be equal to u, right? This is my x, this is my y, and this is supposed to be my z. Okay, so curl of F is kind of very, it's very nice expression here, very simple expression. So curl of F would be just y, which is v, minus x, which is minus u. The third component is 0, scalar product with the TU cross TV. What's my normal vector? My normal vector is 2/5 U, 2/5 V1. 2/5 U, 2/5 v and 1, du dv, and don't forget, this is u squared plus v squared less or equal to 1. So that will be equal to, oops, that will be equal to, well, it's going to be just equal to, if I'm not mistaken, this is a v, right? So it's going to be just 0, right? So this is, otherwise, if it's not 0, guys, of course, you have to use polar coordinates, right? So if it's not 0, use the polar coordinates. But here, it's just a 2/5 uv minus 2/5 uv plus 0 du dv. And so these things here, they cancel out. So the answer here is 0. Okay. So we got the left side. Now what about the right side of the Stokes theorem? So right side. Okay, so now the right side. So we have to part 2. So we have to evaluate the right side of Stokes theorem, and that will be the vector line integral of f along the boundary, right? So along the boundary, so what's the boundary? The boundary is just this circle of radius 1. That's my boundary, right? It's just this circle, and it must be to be constant, to have a consistent orientation with s. So it must be actually counterclockwise. So the boundary is just the circle x squared plus y squared equals to 1. The z is 0, obviously, because the circle lies on the xy plane. So if you want to parameterize, just give me 1 minute, guys. I'm almost done because this is kind of it's very straightforward. So for the boundary here, the parameterization would be cosine of t, sine of t 0, because that's x squared plus y squared equals to 1, and z is 0. Okay, that's my boundary. T between 0 and 2 pi. All right, and so gamma prime of t. So then my integral. So my integral would be. So what's f along the gamma of t? So what's f? F is x z. So z is 0. Z is 0. X squared plus y squared, that's equal to 1, right? Remember, this is my x, this is my y, this is z, and this is f of gamma of t, right? So along gamma of t, the z is 0. So my vector field f was, f was this one here, was the x z y z x squared plus y squared, right? So the z is 0, so that will be 0 0 1. Scalar product with the gamma prime of t. So this should be gamma prime of t here. Right? This is the vector line integral. Gamma prime of t, so it's minus sine of t, cosine of t, and 0. dt t between 0 and 1. And scalar product, so it's going to be just 0. Right? You can see here, this is it's going to be just 0. And that's exactly, so that verifies Stokes' theorem, right? Conclusion. I'm just write down the conclusion, guys, and I'm going to stop. Sorry about that. Conclusion. So the curl of f along s is equal to the vector line integral of f along the boundary. So both are equal to 0. So Stokes' theorem is verified. All right, guys, I'm gonna stop here. As I said, first, well, I wish you good luck for the test. So test is gonna be on Tuesday at 10 a.m. from 10 a.m. to 12. And then Thursday, I'm gonna cover Gauss theorem. And if we have time, then I'm gonna do like a small, a short review for the final. And again, the final, it's May 25th. And it's just your first test plus second test plus Gauss theorem. Okay. Thank you, everyone. And I wish you, please don't forget your homework number 6, I think. And it's due today, right? Thank you, everyone.
Thank you, Professor.
I will see you next Tuesday. All right. Take care. Take care, everyone.
Thank you, Professor.
Thank you, David. Thank you, Enrique.
Professor, I have
Yes.
short questions about something
Yes.
for you, Dave. Okay. So for number 5, so I was finding the area of the hypospheroid, right? And I saw that you gave an example, but what you did was that you have half the line integral
Yeah.
dy minus y dx. That's the formula that I should use for number 5.
Yes, for number 5, it's minus y dx. Yes,
Half.
number 5. Let me write it for you here. It's half minus y dx plus x dy. So in this case, so the y, so y is a sine cube, right? So it's like saying it's minus sine cube of t dx. So this is like, because here you take derivative with respect to t times dt. So times dt here. So derivative of x with respect to t would be like 3 sine, yeah. So this should be like times like 3 sine cosine square,
Yeah.
right? Plus, and then you have x, which is cosine cube, and then dy. So it's dy dt. So derivative of y with respect to t. So that's like 3 cosine t sine square, right? I think it's gonna be
Like that. But then when I went and like researched what the area of what a hypocycloid should be, they said that it should be 3 pi over 8. But then I would have 3 pi over 8 times a half. So that's why I wasn't really too sure.
okay. I see.
So should it be 3 pi over 8, or am I correct with the half times 3 pi over
No,
8?
you're correct with the half.
Okay, so it should be 3 pi over 16.
Well, I don't know the answer, but if you say so, yes. But you need the half.
All right, then just okay. And for number 8, so for number 7, it's basically the same question, just different things. So for number 7, I did the point B minus point A to get
Yes. Yes. So if you
for
do
number
the
8, how would I do that now with the curve? What would I do?
no, number 8, the thing is, this is like homework number 5. So number 8, because your vector field is conservative by number 6, right? So then here you have to integrate along a simple closed curve. So in that case, if it's closed, it means that the terminal and the initial points are the same. So that's like f of b minus f of b. So that'll be like 0. So
the answer should be 0.
Yeah.
Okay.
The answer is 0 because you have to justify your answer, right? Because f is conservative, so then f is a path independent line integral. So the integral will be f of b or minus f of b, so that'll be 0.
Okay, thank you. Those are my only.
Okay, that's good. It's I spend the time
the Stokes theorem, it's harder than the Green's theorem. So
yeah, that's true.
Thank you,
All
Professor.
right. Thank you, Anicia. Take care. Wish you good luck and stay safe. Thank you.